Right, one of the first things that we need to understand is that, well, one of the most important things you need to remember is that force is a vector quantity. Okay, so the important thing with a vector quantity is that a vector has two components, right? It has magnitude, so some kind of size, and very importantly, it has direction. Okay. So one interesting thing with vectors is that when we have two or more vectors, right, acting on something or acting in general, we can combine vectors to create a single vector, right? And so the easiest way I want you to think about this is think about vector f, right? I tell you to walk in that direction, and the length of the vector is a certain amount of meters, right? So I say walk in that direction for that many meters, okay? When you get there, I want you to turn and I want you to point in direction of vector g, and I want you to walk the length of that vector in meters. Now you can see in my example, the lengths are different. That tells me the magnitude is different for those two vectors. So Kiana, if you were clever and I gave you the instructions, there goes my screen share. Okay, so anyways, Kiana, if you were a clever child and I gave you the vectors beforehand, what would you do to cheat if I told you these are the two directions you have to walk in? We're in a flat open area.
You do them together if they're opposing?
Yeah, well, if I was clever, I'd think, well, I have to walk all the way down from where I am to the point where the end of F is, and then I have to walk up in that direction. So what I'll do is I'm just going to walk straight to the end of G. So I'm just going to go from here to there.
Yeah.
So now I have a vector F plus G, okay? So that's the wonderful thing about vectors is we can add vectors together to get a single vector. So instead of going, in our example, all the way down from F and then all the way up to G, okay? We can combine and go straight there, right? Now I can actually move, right? Sometimes you can have, if this was a force vector, you can have a vector where forces are acting on the object in different directions, right? And instead of representing the force as two separate vectors, okay, we could combine the vectors to give us the net force, right? Which would again just be that vector Fg. Okay. Now this is a very important piece of information because if we can combine vectors, that means we can also split vectors up, right? And this is what we do when we are resolving forces in two directions. We are actually going to take a single vector. If it's not a vertical or a horizontal vector, we're going to take the vector and we're going to split it into a horizontal and vertical component, right? So let's discuss the idea of components, right? So the components of a vector are where we split the vector into a vertical and horizontal component, okay? The important thing about this split, right, is our two new vectors are always going to be perpendicular in direction. So if I take vector f here, vector f is acting in both a vertical and horizontal direction, right? If I want to split this vector up into its two components, I can do that by breaking it apart, right? So I'm going to have some, no, that didn't want to go. We're going to have some horizontal component, right? We always want to split these things into horizontal and vertical because then we can resolve them later, right? And then I'm also going to split that into a vertical component as well. So I've split my vector up into two components. Now, one of the most important things to remember here is I'm not creating two new vectors, okay? These two new vectors, these two components, they are replacing the one vector, all right? So I don't add some vectors now to my problem. I'm splitting up the vector into two separate components. Now, because the vertical component is usually up and down, okay? And on a Cartesian plane, the vertical component is usually the y component, right? We're going to call this new force y, so the vertical component of my vector. And I'm going to create force x because it's on the horizontal. Usually when we're working horizontally, we talk about the x coordinate, right? So I have force x in the bottom and force y going vertically. So I'm splitting these up into two separate vectors. And the nice thing is you can see they usually form a triangle. Not always, but some of the times. Okay? Especially if we have one vector that we're splitting up into two, we'll always get two components that make that lovely triangle. Right, the only thing we have left to do is find the size of these two new vectors, okay? Because we can't just guess what they are, right? We know what the size of vector f is, okay? What is the size of vector f in my example, Dominic?
Vector f is fx plus fy.
Yeah, well, we're not going to add them. We're trying to work out fx and fy. So the size of vector f is f, right? That is its size, right? Obviously, in reality, I'm not going to give you some letter. I might, right? But usually the vectors follow is given to you as a number. Okay? And now we need to find the size of that vector. So this is a triangle. So Toya, what awesome piece of mathematics do you know about finding sides and angles in triangles?
There's Pythagoras, there's trigonometry rules, and
Okay, so we're going to use the second one that you've mentioned, trigonometry. Okay. Now, because I've split this one vector up into two components, I've actually created an angle here, right? And I'm going to call that angle theta. So let's look at each of my components separately now, right? We'll write the finished ones down over here, but let's do some calculations for the other two, okay? If I look at angle theta, Zara, what trig ratio could I use to find the vertical component or the vertical force, F of y? Okay, which side do I know and what am I trying to find and how does it relate to angle theta?
Are we trying to find?
So we're trying to find, if we look at angle theta, okay, so if I said we have angle theta, what trig ratio can I make that's the easiest one if I consider I know the length of f and I'm trying to find the length of fy, right? The vertical component.
Oh, then that would be f sine theta.
Okay, so it's the sine of theta. So f of, oh, sorry, I don't know why I'm writing in that. F of y is the opposite over the hypotenuse, which is the force, right? The force that I probably know, right? And if you look at that in relation to angle theta, right? That's opposite over hypotenuse, right? And that's just sine. So if I want to solve for the vertical force, I just multiply both sides by the force, right? And this leads to, if I want to find the vertical component, that's just equal to the force times sine theta. Right, and we can do exactly the same thing for the other angle, except this time you can see we have f of x over the hypotenuse. That's cos of theta. That's adjacent over hypotenuse. Okay? And again, if we multiply by both sides, we can find the horizontal component of the force by taking the force and multiplying it by cos theta. Now, just to remind you that if you're given angle theta, right, you can also work out the opposite angle, which is sometimes called angle alpha, okay? Because this is a 90-degree triangle. And so we could also find out these angles or these magnitudes in terms of angle alpha, okay? So if we look at f of x, for instance, in terms of alpha, okay, the side I'm trying to find is the opposite side, right, over the hypotenuse. And so this would be f sine alpha. And f of y would just be f cos alpha. So don't be limited to one angle. Sometimes you need to look at these from different angles, okay? And another important thing just to remember is that theta is equal to 180 degrees minus alpha. No, I'm lying, 90 degrees. And because it's an equation, you can say that alpha is also just equal to cool. Toya, are you happy with that? I believe this is new, probably only to you at the moment.
Yeah, I'm happy so far.
Yeah. So what
It's a
we've
little
done
bit
here,
new to me too. So
is it new to you
with
too,
that's
Dom?
yeah,
Okay, but are you happy with that? Does that make sense to you?
yeah.
Taking a
Yeah,
vert,
yeah.
we're
Definitely happy
taking,
with it.
right? And the only time we do this, guy, if we have a force acting in the horizontal and the vertical direction, if you're given a vertical and a horizontal force, there is no components, right? We are taking any force that is not horizontal and vertical and breaking it up into horizontal and vertical components, right? So an important thing to remember about components, right? They are always at right angles to each other, okay? We could make these, we could consider these two new components at other angles, but then we wouldn't be able to work with them. We'd be comparing apples to bananas later on, right? The reason we want vertical and horizontal components is because then we can resolve things vertically and then we can resolve things horizontally later, okay? And because they're at 90 degrees, the vertical and the horizontal, we can use trigonometry to solve these two components. And obviously, importantly, the original force, the force that we are splitting up, is the hypotenuse in the triangle. Okay? And as I mentioned before, these components are not extra forces, right? They're not some new forces that you are creating. Once we separate a force into its two components, in theory, we ignore the original force after that. because it's now been split up into two separate forces, right? And we could think about that backwards as well. If we are given a vertical and a horizontal force, we can combine the two forces to create one force. So that brings us on to resolving forces. Okay? What we normally do when we're looking at forces in two dimensions is we create equations and we find the net force of the two different components. Okay, so we look at the net result vertically and the net result horizontally. So what do they say? Equations are formed finding the net force and the net force vertically. And when we get to a work example in a minute, this will make a little bit more sense. Okay? So what we are going to do, if we have multiple forces acting on an object in different directions that are not vertical and horizontal, we will split the forces up. So if we have, for instance, a vector going in this direction and a vector going in that direction, right? We have two forces acting on some object with that magnitude and direction, and we want to resolve the forces. We want to find the net force, okay? We would split both of these up into their horizontal and vertical components. And then we would look at these vertical and horizontal components individually. Okay? We would resolve the vertical components, and then we would resolve, the horizontal components. And this process is called resolving the forces. Right, the last thing we need to remember is, well, it's just for the first couple of chapters, we are going to be considering forces in equilibrium. In other words, forces that are stationary or at constant velocity. Okay? Right, and what can you tell me about the forces in equilibrium, Dominic? What could you tell me about the net forces in equilibrium?
Well, the net forces in equilibrium there is no net forces, because if you add all of the forces together, you get zero. That's why they're in equilibrium.
Okay. So importantly, in equilibrium, the net forces, because remember, when we are talking about forces now, we're not looking in one dimension anymore, we're looking at both dimensions. And for an object to be in equilibrium, or in other words, stationary or at constant velocity, the net force in both directions, okay, so I think in the word they like to use both perpendicular directions. Okay, let's have a look at an example. Right, this is the first example in your textbook on page 55. I'll try to make this a bit bigger. Unfortunately, I think the quality of the pirated PDF at this point lost its quality, so it's a bit grainy. So use your textbooks if you're struggling to see on the screen there. Right, so in this question it says a particle of mass 4 kilograms is held in place by a force of magnitude of 100 newtons acting at an angle of theta above the horizontal. Okay, so you need to remember horizontal is left to right, and above just means going up. Okay, so if I hadn't given you a diagram, you would have had to work that out for yourself. Okay? Find the value of theta and f. Okay, so we know that there's this object, right? That is suspended over there, right? Kiana, what is its acceleration if it's held in place?
0.
Its acceleration is 0. Okay? So if it has zero acceleration, what is its net force? Okay. If we consider the equation force, and remember this force, guys, always remember this is not just one force, this is the net force, is equal to mass times acceleration, right? If we have 0 acceleration, right, by virtue of there being no acceleration, there can be no net force. In other words, the net force is 0 or at equilibrium. So if something is held in place, it has no acceleration. So we have the weight of the object to consider. We have the force that's been pulling up and to the right of 100 newtons. And we have another force that's acting horizontally to the left. Okay? And we need to find this force F. Right? So the first thing we do when we look at the problem is we consider this 100 newtons. Okay, it's not acting in a vertical or a horizontal direction. So at the moment, I can't do anything with it, right? So I need to resolve, or I need to split this up into its two components. So I'm just going to quickly there's my 100 newtons. And I'm going to resolve these into two separate forces. Okay, now I'm not adding two extra forces. I'm now splitting the forces up. Okay, I have this angle theta. Right, I also have a force acting in this direction. And I have a force acting in this direction, right? Don't forget that the weight of an object, right, especially when we consider the vertical component, we always need to consider the weight of the object, because regardless of what's going on, that will always remain there, unless we go into space where there is no more gravity to pull you down. Okay. So we were told that the mass of this particle is 4 kilograms, and so its vertical force downwards is 4 times g newtons. Okay, right, and this is a downwards force, right, and we can just consider this to be negative. If you want, you can obviously write this as 40 newtons, right, because we're using 10 as the gravitational constant. Right, now, Zara, looking at this diagram, right, if my forces are in equilibrium, what can you tell me about the two vertical forces? Right, what can you tell me about the two vertical forces?
They add up to 100 newtons.
Okay, they don't add up to 100 newtons.
I mean, not add up, but rather.
So I want to
They
consider this force here and this force here, all right? Because remember, I'm not considering the 100 newtons anymore. I've split it up now into a vertical and a horizontal. Because now that I've split it up into vertical and horizontal, I can work with it. Okay? So what I want you to remember is that if this object is not in motion, that means its net vertical component is 0. Okay. And because we only have these two forces, that means the downward force, the 40 newtons down, there must be an equal and opposite upwards force in order for it to be in equilibrium. Okay, does that make sense to everybody?
Yep.
Yeah. So if we consider down to be negative, so we have minus 40 newtons going down, that means that the size of my vertical force upwards must be positive 40 newtons, right? That's the only way that these vertical components could be in equilibrium, if the two forces were equal and opposite. So now that I know what the vertical component is of my component forces, I can actually go and work out what angle theta is because I've got two sides, right? And if you have the length of two sides in a right angle triangle using some trigonometry, you can work that out, okay? So if I wanted to work out angle theta, I have the opposite side and I have the hypotenuse. So the sine of theta is equal to opposite over hypotenuse. And if I want to find theta, I can just take sine inverse. And that's going to give me 23.6 degrees. Okay, which you will store in your calculator, obviously, because we want to keep the most accurate answer. Right, Twaya, what can you tell me about the horizontal components? This object is stationary, it's not moving. What can you tell me about the horizontal components? What can you tell me about their net force?
Stationary.
Well, it's stationary, so their net forces, there must be a net force of what? Zero. Okay. If an object is stationary, that means that their net forces in both directions must be zero. So that means that this force F acting in the left-hand direction and the component force, the horizontal component force of my 100 newtons, they must be the same magnitude. They're just going to be acting in opposite directions, right? So if I can work out what the horizontal component is of this force that I've split up, I can work out what the force in the opposite direction is, because they must be the same, they'll just be in the different direction. And that length, so this length of this force, right, that's the adjacent side to the angle that I know, and I know the hypotenuse of 100 newtons. And so I can work out, right, if I'm working out the horizontal, we can also just remember our little formula, right? If I want the horizontal component, right, it's the force, right, which is 100 newtons. And cos theta, which is 23.6 degrees. That's going to give me 91.7. Okay. So this component force is 91.7. So if that force is 91.7, then Dominic, what is the size of force F that I'm trying to find?
minus 91.7.
Okay. Well, we don't know if it's minus or plus because we haven't specified in which direction is positive on the horizontal. Okay. So the size of the force, okay, we were asked to find the size. So that's just the magnitude, and the magnitude of that force is 91.7 newtons in the direction that the arrow is pointing.